Welcome to Study Loop.
Question number 24 calls a little bit back to another chapter in the book, so be sure to check that part out just in case I mentioned something that you don't recognize. But we have a long copper strip that is said to be 1.8 centimeters wide and 1 millimeter thick, which there's no way I'm going to draw that well. So let's pretend I did. So yeah, it's 1 millimeter thick, and it's placed into a 1.2 Tesla magnetic field, as in a figure 20-21A in the book. I'm not going to draw that because it will do much better than I can. But whenever a steady current of 15 amps passes through it, the Hall EMF, electromotive force, is measured to be, let me write this down, is measured to be 1.02 microvolts. And the question wants us to find a couple things. First, for part A, it wants us to determine the drift velocity of the electrons. And for part B, we want to find the density of free electrons in the copper. So for part A, the drift velocity can be found from the equation here, where our Hall EMF there is equal to the drift velocity times the magnetic field times the distance there. And then I realize this is a very poor picture that I've drawn here. So yeah, the one in the book is going to be much better than this because our electrons are flowing all this way. But moving this around to get our drift velocity, it is equal to the magnetic field. Is equal to the EMF, the Hall EMF, divided by the magnetic field times the distance that it's traveling there. And this, if you plug in, you'll see it is roughly 4.7 times 10 to the minus 5 meters per second. I have truncated it here. But the tricky part here, because it's not in this section, is part B, because you need to go back to chapter 18 and read through the section, and you'll find that in equation, I'll write it here, in equation 18-10, you have an expression for the number of free electrons, and it is defined as this. So N is equal to I divided by E, making sure I have all the right constants here, A, which is our area, times the drift velocity. So this is simply an expression that utilizes the fact that you have a current, which is charge per second, and then at the bottom you have the charge that is flowing through a given plane, if you will. So that's how you can interpret this equation. And the current here is given in the problem as 15 amps. And the area is going to be 1 millimeter times 1.8 8 centimeters. And if you plug all this in, you get that your number of free electrons in the copper is 1.1 times 10 to the 29th power. And the units there are electrons per meters cubed. So quite a few electrons are flowing through this little bit of wire, if you will.